Can you hear me?
Absolutely. Yep.
Yeah, great. Greetings from my kitchen in Detroit. I'm Baptiste. I work with Echek Menef at Wayne State, and I'd like to thank big thanks to all the organizers for this great conference. It's really nice to see all this science and all the people behind it to actually branch out from the parahydrogen effect. So what I want to just briefly show you is about something that I had never heard about like a year ago. Another triangle, maybe hopefully virtuous, from laser to maser to maser to Razer. In the case of parahydrogen, here we are talking about proton Razer. And this is a quantum mechanical effect of radio frequency amplification by stimulated emission radiation that we observe very easily with parahydrogen-induced polarization, and that you might observe as well in your lab. Next, please. So our FIP studies at Wayne, the most basic studies we can do. We will do this in the liquid phase. We're gonna use our parahydrogen to cool down hydrogen, and from our parahydrogen generator to get some like nearly pure parahydrogen gas, bubble it through some solutions and study the pairwise addition reactions with various substrates, catalysts to characterize the hyperpolarized products and to develop new techniques for polarization transfer towards heteronuclease. So Nuwandi yesterday presented you some data about diethyl ether, the formation of hyperpolarized diethyl ether, where we can monitor the hydrogenation kinetics, the polarization buildup, the lifetime, and also because here we are talking about very volatile compounds that we would like to use to test as inhalable contrast agents. Also, we can monitor the evaporation of this compound, and to do this, we use a commercial benchtop NMR spectrometer at 61 megahertz. Next, please. So, if I show you a series of spectra for diethyl ether. In black, here we have a thermally polarized diethyl ether with the CH2 group at around 4 ppm and the CH3 group at around 1 ppm. So this is using this is standard using a 90-degree pulse. Now, if I look at a slightly hyperpolarized spectrum, I will have the well-known antiphase pattern with two features of nearly equal intensities. And then when we raise the polarization of the sample, we're gonna start to see interesting effects such as this pink spectrum, where we have a broadening of the CH2 region and a narrowing of the CH3 region. And superimposed on this spectrum, on this spectra in red, I also show here what we are interested about here. It's a spectrum recorded without any excitation pulse by leaving the
30 seconds.
The receiver open for 30 seconds, and we see these two very broad no, these two very narrow features which fall down to around 0 ppm. Next, please. And so behind this are absolutely huge signals which show chaotic features, frequency combs, two-mode Razer, and which dies out as single-mode Razers that we can observe in Altadena or Pasadena conditions, and that give access actually to J-coupling constants in the case of Altadena, and in the case of Pasadena to a chemical shift difference. So next.
Baptiste, I have to cut you off there. So if you want more information, you will go to the poster. I'm sorry. Okay, the next speaker is Fraser, I believe. Yes. So let's just, okay. The floor is yours.
Cool. Thanks for the introduction. So I work with Dr. Megan Hales at the University of York, and I'm going to talk to you for a couple of slides about some work we're doing to look into Saber processes in situ to the magnetic, in situ. Next slide, please. So as you guys probably have all seen throughout the week, you've probably seen a number of videos of people doing Saber at high field, but the general sort of traditional Saber experiment is you have some form of NMR tube filled with parahydrogen, your catalyst and substrate. You shake that in a given polarization transfer field, you build up a substrate polarization, and then you transfer that to your NMR magnet where you get these, and you get these beautiful, highly enhanced spectra out. The sort of issue that comes with or the complexity that comes with these experiments is that your polarization transfer field, your polarization transfer is performed at a different field, a different location, so you have this complexity of the transfer into your magnet. Next slide, please. So what we're trying to do in Megan's lab is develop an instrument that we can use to look at the Saber processes in situ to the field, fully in situ, so removing the complexity of the transfer. So this is sort of a general schematic of one of the bit of the instrument that we put together, and sort of comprises of the major components of a liquid nitrogen-based parahydrogen generator, a automated flow system that can be controlled via our NMR spectrometer, which is a Magritech Terra Nova NMR device that we've modified for this purpose, which is in turn all based and in turn controlled from a Arduino Mega and associated LabVIEW interface. So on the bottom of this in situ NMR bit is a little flow cell, which is what our Saber, which is our Saber flow cell, in which we have around 4 milliliters of Saber solution, and we bubble parahydrogen through with through a porous frit to get it into solution. The Terra Nova NMR device has a big electromagnet on the outside that we can use to apply a polarization transfer field, or apply a polarization transfer field. And we have these additional field correcting coils and RF shielding that we've got around it, which I'll talk on now. If you go to the next slide, please. So one of the oddities or complexities of the Earth field NMR is your bulk field, your BE in this case, doesn't necessarily point, or isn't necessarily orthogonal to your B1 coil. So depending on where you are on the Earth, it will point in a slightly random direction. So one of the things we put a reasonable amount of work in is methods of correcting this. So via the addition of an additional field, we can nicely orthogonalize our system, which in turn allows us to produce nice, accurate nutation curves, which is just shown next to them. And oh, sorry, go back one slide. And the rationale for putting this effort in to get these nice nutation curves is it lets us do these more complex experiments. So this is a variable flip angle hyperpolarized lifetime measurement, a single shot lifetime measurement. And just on the bottom right, I'm showing sort of a comparison between these single shot measurements to that of a more traditional pseudo 2D style measurement. And this is T1 as a function of equivalence in or substrate to catalyst ratio. So as you go to a higher substrate to catalyst ratio, you have more signal coming from your bulk solution, which leads to a longer bulk T1. And we can see that this matches up quite nicely, aside from one odd point. Next slide, please. So the rationale for trying to do this is to look into the look a bit more into the sort of the chemistry and the physics of what's going on during the activation process. So this on the top left is just showing a simplified catalyst activation process. And so in a typical Sabre experiment, you'd start with some description of pre-catalyst, which you then activate via the addition of substrate and parahydrogen. And over time of parahydrogen bubbling, it would become active.
30 seconds remaining.
Cool, thanks. So on the graph, I'm just showing the normalized intensity in the red dots. As your catalyst activates, you have higher Sabre efficiency and hence higher signal intensity out. And in turn, we see a trend in the T1 of the T1 decreasing as the catalyst activates. But we're currently battling SNR for that and trying to improve that now. Cool, thank you.
Well done. That was right down to the wire. Thank you.
Perfect.
Now remember, all of the poster presenters have a full 1 hour session, so that's why we're keeping it to 5 minutes. We're ready with our next speaker. Great.
Thank you. What is Sabre? Let's start from this shortly. Next slide. Sabre is the method of hyperpolarization which uses parahydrogen as a source of hyperpolarization. It doesn't require hydrogenation of the target molecule, and it provides renewable hyperpolarization over a timescale of tens of seconds with the addition of fresh parahydrogen. So we can obtain hyperpolarized biomolecules such as nitrogen heterocycles, pyridine, imidazole derivatives, and many others. Moreover, if we have isotopically labeled biomolecule, we potentially can use it as contrast agent. Thus, the aim of this work is a synthesis of nitrogen-15 labeled biomolecules. Next, please. Metronidazole is an FDA-approved antibiotic belonging to the nitramidazole class of compounds. First, 2-methylimidazole was prepared by using labeled ammonium chloride as the N15 source. In the second step, we carried out nitration reaction using labeled sodium nitrate as a second inexpensive N15 source. Ethylene oxide was employed in the last step to introduce the hydroxyethyl moiety. The overall yield over 3 steps was around 15%. Next, please. Next biomolecule is nimerazole, which has been originally developed as a safe antibiotic against anaerobic infections. We performed the synthesis of isotopically labeled nimerazole. In the first step, labeled imidazole was prepared with 60% yield via condensation of glyoxal formaldehyde and labeled ammonium chloride. Subsequent nitration with N15 nitric acid allowed to obtain nitramidazole with 30% yield. This compound was alkylated with morpholine derivative in the presence of potassium carbonate, and due to unselective alkylation in this case, the yield of nimerazole was only 20%, while the yield of its isomer was 60% in the last step. Next, please. The third biomolecule is 4-aminopyridine, which is used as a research tool in characterizing subtypes of the potassium channels. We synthesized this compound using ammonium chloride as the first step to obtain N15 pyridine with 60% yield. Then pyridine was converted into the product through the 3 steps, including oxidation by hydrogen peroxide, nitration, and reduction by iron in acetic acid. The last step turned out to be very challenging for us because the reaction is strong sensitive to quality of iron, and we got a wide range of yields from 5 to 85%. Next slide. You can see on this picture there was a result of a violent reaction in our hood. The right picture demonstrated how the hood should be looked normally. Next, please. Thus, despite of different challenges, we synthesized 3 nitrogen-15 labeled compounds. It allowed us to collect experiment material for papers. Next, please. At the end, I say thanks to the people who inspired me to do this working, especially Kirill and Eduard, who made it possible. Thank you all for this meeting.
Great, thank you very much. The next speaker is here. Fantastic. Let's get your slides up. Great.
Thank you for this opportunity. I would like to present our recent work with azobenzene molecule in zero field. Next slide, please. So azobenzene molecule is shown on this slide. It has an interesting property that it can be photo switched between 2 isomers. Trans azobenzene is a stable form, but then using ultraviolet light, it can be quickly photo switched to cis isomers, which is metastable, but still it can exist for days in solution. And it then can be quickly switched to trans azobenzene using blue light. And this photo switching can be repeated for many times. And next slide, please. The same molecule actually is interesting from NMR perspective, especially if we consider a nitrogen-15 labeled component. For instance, trans azobenzene, nitrogen-15 spin pair exhibits a long-lived state. So singlet pair of this singlet state of this pair is long-lived. And cis azobenzene can be efficiently hyperpolarized using Saber technique. So our idea in this work is to try to perform hyperpolarization of cis azobenzene, then photo switch it to trans configuration and store hyperpolarization in long-lived state of trans N15 spins. Next slide, please. So singlet lifetime of the trans azobenzene is pretty unique because it has a very long-lived lifetimes of 17 minutes at actually very high magnetic fields. So here you can see that at a field of 16.4 Tesla, it's 17 minutes. And another interesting feature is that because of symmetry of the spin system, this singlet state of N15 spins can be detected on nitrogen-15 channel, but also on proton channel, which makes this molecule probably very interesting for magnetic resonance imaging applications. Next slide, please. So on the other hand, Saber sheet can be used for efficient hyperpolarization of this isomer. And we optimized conditions and studied few dependencies of these processes. And especially we studied dependence of T1 relaxation time. And it appeared that for Saber solution at 500 nanotesla, this azobenzene relaxes pretty fast. So it has a relaxation time of 7 seconds. But at the same conditions, in the same solution, trans azobenzene actually has a T1 relaxation time of approximately 2 minutes, which makes it pretty perspective in terms of experiment of hyperpolarization and photo switching, because it is possible to accumulate trans azobenzene while performing Saber and shining simultaneously. So now we're actually preparing these experiments. And with that, please next slide. I would like to thank my supervisors and co-workers Alexandra Yurkovskaya, Konstantin Ivanov, Alexei Kirutin, and Vitaly Kozinenko from Novosibirsk, Hans-Martin Fied and Gerbert Zimmermann from Germany. And thank you for your attention.
Thank you very much. That sounds like exciting work. I know all of the posters so far are amazing. Remember that we have an hour to visit with each of the poster presenters, so I apologize if people think I'm being overly harsh in keeping people to time, but we think it's really the best way in an environment like this for people to get a sort of flavor for the work and then be able to move back and forth between posters. So please don't take it personally. Okay, our next poster presenter is here. 5 minutes.
Oh, hi everyone. Before I start, I would like to say how great is that in such difficult circumstances, the place that unites researchers all over the world, and we can share our research. And the most exciting thing that the PERM hydrogen community has now its own conference. I hope that this conference will continue in the future. And today I'll talk about the results that we have been obtained in Mainz in collaboration with Professor Budke group. And next slide, please. I think none of those present needs to be convinced that NMR spectroscopy is a super powerful analytical method for investigation of various materials, structure, and so on. And NMR strong suit is that NMR has extraordinary chemical specificity, and because of this, nowadays NMR is widely used for reaction monitoring online, and NMR provides chemical information about the sample in a qualitative and non-invasive manner. And for example, recently Magritech introduced a commercially available NMR benchtop for the reaction monitoring in the fume hood. Next slide, please. However, conventional NMR spectrometers are usually inconvenient for certain application, and this method cannot be used for observed chemical reaction in metal containers because the metal prevent error of penetration, and for this reason, NMR sample containers are typically made of glass, plastic, or ceramics. Another significant limitation is that resolution of high field NMR spectra of heterogeneous samples is seriously hampered due to susceptibility induced broadening, and heterogeneous samples surround us, frankly speaking, everywhere. And the most industrially relevant example is that catalyst and catalytic reactors. So that is why a lot of efforts are directed to design NMR compatible reactors, as my colleagues told yesterday. Next slide, please. And but if magnetic field induce such difficulties for studying heterogeneous samples, what happens? We can just do NMR in the absence of magnetic field. So alternative is ZOLF NMR, in which the NMR is performed in the absence of applied strong magnetic field. In this regime, there is no chemical shift, but the structure information can be retrieved from the highly resolved lines in J spectra, and because a J couplings interaction is mediated by electrons, and so J couplings network is super sensitive in changes in molecular geometry and electronic structure. So next slide, please. The main drawback is ZULF is super low sensitivity, and for ZULF, the sensitivity problem is more acute than ever. But PER hydrogen-induced polarization can be also used in the zero field, and this field is actively developing. So the FIB at zero field was observed only 9 years ago, and by Thomas Theis and Mieter Butker and Alex Pines. Next slide, please. Here in this work, we show that we can not only acquire the J spectra, but we also can monitor the chemical transformation at zero field. And the model reaction, we used two-step hydrogenation of dimethyl dicarboxylate with perohydrogen and producing malleate, and the product is succinate. Next slide, please.
You have about 10 seconds.
Okay, so in this slide, you can see the J spectra of malleate and succinate at zero field. And the next slide, please. This reaction was monitored at the zero field and the different pressures, and we see the nice plots at the left, and this show us, it's next slide, please. Also,
we have to cut it off there. I'm sorry. It's brutal, but we have to do that. But remember, we have an hour afterwards to continue. So the next speaker is Matheus, I believe. Yes. Fantastic.
Hi. Can you hear me?
Yes, absolutely.
Hi. So I'm Matheus Rossetto. I'm a second-year PhD student under the supervision of Megan House. And at the University of York, and I'll be talking to you about probing Saber polarization transfer to heteronuclei with Earth-Sword NMR. Next slide, please. So I begin by showing our Earth-Sword NMR setup, which allows us to perform Saber hyperpolarization in situ of the detection field, which in this case is the Earth's magnetic field. Typically, Saber is carried out with detection at high fields on high-field NMR systems, where the polarization transfer step and detection step occur separately in space and time, because the polarization transfer step requires fields in the microtesla to millitesla range. In situ detection is very important to us because we want to study the Saber process, the chemistry and physics behind it. In more detail, and more specifically for my project, I'm looking at optimizing polarization transfer to heteronuclei, starting with fluorine. By being able to observe and detect what's happening as soon as the parahydrogen comes into contact with the catalyst, we hope to get more detail and study what's going on. Earthfield helps us to do this, and because of it allows us to do in situ, which I'll explain later. But it's also very useful because not only do we not have to generate this field, it's already available to us, but it's also very homogeneous, and so we can achieve sub-Hertz line with resolution of our hyperpolarized signals. Next slide, please. So how does the in-situ Saber, how do we achieve it? Well, we have these two coils. I show the polarizing coil above there on our Terra Nova Earthfield probe. It's a built-in coil. And we have these Helmholtz coils, which I show below. By passing current through these coils, we can achieve magnetic fields in the polarization transfer field range. If the field is turned on during parahydrogen bubbling during our experiment and then switched off adiabatically, we can then excite and detect the hyperpolarized spins with the Earth's magnetic field. We use the polarizing coil to produce fields above the Earth's magnetic field, mainly for homonuclear polarization transfer, but then we can also use the Helmholtz coils to counteract the Earth's magnetic field and go below it for heteronuclear polarization transfer. Next slide, please. So we started with the 3-fluoropyridine substrate, which is a well-established Saber substrate, and we successfully detected hyperpolarized proton signals showing strong proton-proton fluorine coupling. However, we did not manage to observe the fluorine signal. This is mainly because the fluorine couples to 4 other protons, and so if this fluorine was being hyperpolarized, there's a very weak and broad signal hidden under the noise somewhere. And so because of this, next slide please, we moved on to this substrate, 3,5-bis trifluoromethylpyridine, which essentially just has more fluorines and less protons, and so there's a simpler coupling network, and we hoped this would maximize the fluorine signal, which it did. And we managed to hyperpolarize both nuclei and at 2 different polarization transfer fields. And this you can clearly see that a different state on the fluorine has been hyperpolarized with the different field. And this just shows the kind of extra information that we can achieve with this in situ detection at the S field, and also how we have a good enough resolution to analyze and try and work with this. I also like to note that we use spinach simulations as a tool to help us interpret our spectra that lack chemical shift resolution. Yeah, thank you for listening.
Great, thank you so much for everyone keeping the time. Our next speaker, okay, we'll go right to it. 5 minutes. And I just want to remind everybody, again, each of the posters has their own link. The links were in an email, and then they're also in the general channel on the Slack channel, and we'll be able to spend an hour with each of the speakers. Okay, go ahead whenever you're ready.
Thank you. Good morning, everyone. So I am Mohammad Kabir. I am working with Dr. Chukanov in Mainz State University. So my project is about hyperpolarization of two metronidazole isotope logs and quadrupolar sinks effects. Let's see. Next slide, please. So in this figure, we see the figure C and D are the structure of N2. So C is N2, where we labeled two nitrogen as N15 and one is N14, and the D structure is where we labeled all the three nitrogen, which is N3. And we see the H figure, which is about the experimental layout. So we did a simple experiment. So we prepared the parahydrogen, and then we prepared the sample of N2 and N3, and we poured it in the enema tube and ran through the parahydrogen, and we got data from the benchtop enema, and we found for M3 we see the peaks in F figure, and for N2 figure peaks like G. Next slide, please. So for the optimization for both the substrates, so you found that in case of N3 and N2, the magnetic field is 0.4 microtesla, where we got our higher polarization, and for the room temperature is the best for the polarization buildup, and for if we see the flow rate, so 70 to 80 SCCM is best for the polarization. And for the catalyst activation, it took around 2 hours for both chemicals. So next slide, please. So we measured the TB buildup and T1 relaxation in 0.4 microtesla and 1.4 Tesla. So what we found that in both cases of N2 and N3, the TB value in N3 is much more higher than the TB value of N2. And in case of T1 relaxation at 0.4 microtesla, we found that T1 value at N3 metronidazole isotope logs is threefold higher than the T1 value of N2. And but in case of 0.4 Tesla, we found that the T1 value is similar for both N2 and N3. And if we see the graph in figure A and B, that in the middle, that the T1 relaxation versus the polarization, they're supporting the idea the polarization in case of N3 is higher for both all the nitrogen labeled one, and for N2 is lower. Next slide, please. So we figure out that in case of the catalyst activity, where we see the decay for A and B, there are kind of dependence linearly, and in case of buildup, there are some kind of showing the agreement with the decay, because we see that in case of lower concentration, they are showing maximum better T1 and TB value, but the lower polarization, and for better or higher concentration, their value is kind of reverse. And next slide, please. So from our experiment, we concluded that the 2 bond and 15 J couplings happening because of the efficient transfer, and in N2 metronidazole isoprenols, it has 14 and 14 nitrogen, which is bad for the T1 relaxation because they have the quadrupolar spins effect, and we saw the catalytic effect is higher concentration is best for the T1, but lower concentration of catalyst is best for the T1 value. And comparison with both the compounds, we figure out that N3 metronidazole isotope lux is better than the N2 metronidazole isotope lux. So that is the end of my presentation. See you in the poster session. Thank you.
Thank you very much. Okay, our next speaker. Go ahead whenever you're ready.
Yeah, I'm ready. Hello, my name is Aminata Sakho. I am a second-year PhD student at the University of York, and I'm co-supervised by Dr. Megan Hals and Professor Simon Dyke. I will talk about optimizing the cyber popularization of amine using the in situ field NMR. Next slide, please. I will begin to show the motivation of this work. First of all, amine are interesting because they have been shown in this paper published in 2018 in our group that they are hyperpolarized by cyber using high-field instrument. It is also an hyperpolarization carrier and allows cyber hyperpolarization of new classes of compound which does not bind to the metal sensor. Like it has allowed this version of cyber called cyber relay has allowed to hyperpolarize alcohol, carboxylic acid, phosphate, and phosphonate. The hyperpolarization is related thanks to the exchangeable proton of amine and of the target. In this study, we investigate the use of co-ligand DMSO to optimize the cyber hyperpolarization of benzylamine and other amine using the earth field NMR detection. And in parallel, high field instrument has been used to investigate the effect of the co-ligand on the cyber hyperpolarization of amine. Next slide, please. In this graph, I show two activation curves of benzylamine. Where in green we have added DMSO as co-ligand, and in pink there is no co-ligand. And obviously, we can see that the presence of the DMSO increased the hyperpolarization level gained on benzylamine of a factor approximately of 3. In parallel, we did some high-field characterization, and this allowed to determine the active cyber catalyst form in both cases. In the absence of DMSO, it is the TIS complex, which are commonly seen in the cyber active catalyst, whereas in the presence of DMSO, the complex form is the neutral complex, where the chlorine atom and the benzylamine are bound to the Kailai, and the DMSO is bound to the Kabir. We can see this resonance in the resonance in the highlight region of the proton spectrum. The same high field probing also we did with 1H1B XT spectroscopy has enabled us to highlight the substrate dissociation rate of this complex. In fact, benzylamine exchange rate is increased in the presence of DMSO. In the presence of DMSO, where in the presence of DMSO, and the exchange rate is close to the 4.5 second minus 1 described in the literature to be the optimal exchange rate regime for the classical PDD. And this is the exchange rate is linked to the optimal regime by the presence of DMSO. Next slide, please. And thank you for listening, and I will answer questions in the breakout session, in the poster session. Thank you.
Thank you so much for that presentation. Okay, the next speaker.
Hi, can you hear me?
Absolutely, we can.
Brilliant. Thank you for this opportunity. My project is looking at performing reaction monitoring in a robust and quantitative manner at low field. And the aim of this is to look at photochemical reactions in the end. Why do we want to reaction monitor at low field? Well, they're permanent magnet-based spectrometers, so they tend to be far more portable and say can be used for in-fume cupboard applications. They're also independently locked, which means that we can use proto-solvent systems, which increases the industrial viability of these systems. However, moving to a lower field obviously has some additional challenges, one of the main ones being an increased experimental insensitivity. In my case, I'll be using FIP to overcome this with the reaction of parahydrogen with an unsaturated metal center. Next slide, please. So to develop a reaction monitoring procedure, I used a model reaction, in this case, the addition of parahydrogen to Vasquez complex. I chose this because it's irreversible at the temperature of the spectrometer, and also under the conditions used, there are pseudo first order kinetics, so it's nice and simple. To monitor the reaction, I recorded a proton spectrum every 5 seconds, measured the hydride integrals and plotted those against time. What that tells me is the FIP activity of the reaction over time, which decays as we consume our starting material. To then get out a rate constant, what we do is we accumulate this data, we scale it to the known final concentration of the system, and fit it to a mono-exponential recovery to get an observed rate constant. Using this rate constant and the known amount of dissolved parahydrogen, we can then get out a full rate constant for this reaction. Compared to rates found in the literature, it came out really nice and sort of was valid in that sense. I really wanted to test whether other experimental parameters could potentially skew this rate. So that's what I'm going to talk about a bit now. Next slide, please. In my first studies, I was looking at polarization. In the first case, I looked at whether the formation of a thermal product throughout the reaction could start to affect my hydride integrals. How I did this was I used an OPSI pulse sequence to selectively detect the hyperpolarized signal during the reaction. When I compared my pulse and collect and OPSI experiments, I found that the decay of hydride signal was pretty much identical, and so thermal polarization buildup wasn't having a large impact in the system. Next, I looked at some FIP signal. Next, I looked at some FIP signal results, and in the first case, I looked at whether the size of the acquisition window could affect the rate, as in the 5-second window prior to acquisition, you could get formation of product and subsequent relaxation before detection. To investigate this, I changed the size of the window between 1 and 5 seconds, and what I saw was that relaxation wasn't having a large effect, as K-OBS wasn't varying with this change in window size. The second effect that I looked at was whether some leftover FIP signal, because the 45-degree pulse isn't entirely efficient in killing all the hyperpolarized signal, whether this could affect the next acquisition window. For this, I used some simulations using the equation shown, and I repeated this with several different amounts of leftover FIP signal. I found that the kinetics were pretty consistent across all leftover options, and so this had a negligible impact too. Next slide, please. So the final area that I want to talk about today was that the formation of a temperature gradient during the reaction could skew your kinetics. Say if your sample is put in at a colder temperature, then re-equilibrates in the spectrometer during the reaction. To see if a temperature gradient would form, I used a methanol NMR thermometer. Here, the difference in chemical shift between the two methanol peaks can be correlated to an absolute temperature. When I did this for my original procedure, I saw that there was a 5-degree gradient formed across my sample, which is clearly quite worrying. When I looked at reasons why this might exist, I found 2 main ones. One, that walking to the parahydrogen rig exposes the sample to lab temperature, and so I decided to carry my sample in a thermally insulated holder. And secondly, addition of the power hydrogen, because it's at room temperature, would also create a gradient. And so now I allow 10-minute re-equilibration within the spectrometer. And this is possible as there's limited passive diffusion of power hydrogen into my sample before shaking. By making these changes, I was able to get the gray line shown on the temperature study and have less than 1 degree gradient. And as you can see from the new concentration curve, it still fits nicely, and the rate constant is still pretty consistent. So I'm quite happy that my method is valid and robust, and I'm looking forward to looking at photochemical systems. Thank you for listening.
Thank you so much. Okay, our next speaker.
Yes, thank you for the introduction. So today I'm going to talk to you all about some of the work we've been doing in the FOUT lab at the University of Illinois surrounding the development of cobalt catalysts as Saber catalysts. And so this is really motivated by the fact that, next slide please, our group wants to develop first row transition metals that are able to do similar reactivity as you can see with second and third row transition metals. So if you look at some of the benchmark catalysts for Altadene and Saber, you have a rhodium catalyst and an iridium-based catalyst. Some of the drawbacks with using those types of metals are their potential toxicity, the environmental impact when you think about extracting them from the earth, as well as the cost associated with them. And so our group solution through the years has been to use this pincer cobalt-1 complex, and we have shown it in hydrogenation that you've seen in Allison's presentation yesterday, as well as an Altadene catalyst. So next slide. So my research wanted to look at, can we develop this as a Saber catalyst as well? So looking at the types of substrates that our group normally use with this types of catalysts, I turned towards olefins first to see if we're able to get any Saber chemistry out of that. Next slide. So taking fluorofluorostyrene kind of as a sample substrate and looking at it on various nuclei, starting with the proton nuclei, we took about 64 millimolar solution of fluorofluorostyrene in the presence of catalyst and 4 atmospheres of pure hydrogen. And using the shake and drop method, we're able to observe both a bit of the Altadene product as well as the Saber product here. And so we see with this substrate, introducing pure hydrogen at about 50 gauss, we get up to 80-fold signal enhancement. We wanted to see if we're able to transfer that enhancement to heteronuclei without the use of labeling or magnetic shielding. So we looked at the carbon-13 nuclei. Next slide, please. Or before we get there, just looking at the decay of this polarization. It doesn't last very long with this substrate. Other substrates, you see much longer polarization. So next slide. Going to the carbon-13 nuclei, treating it under the same exact conditions, except we introduce pure hydrogen now at Earth's magnetic field, so pretty far away from the magnet. Shake the pure hydrogen into the solution, run it to the magnet, and take a scan. And so on the top, we have a blue spectrum, which is the thermal spectrum of a 350 millimolar solution averaged at about 2,000 transients. And below that is our single transient NMR experiment. And so with that, we get about 38-fold signal enhancement. Next slide. Looking at the fluorine-19 spectrum, we see both polarization of the Saber and Altadene product. And although the enhancement wasn't great, we did see polarization transfer to over 7 bonds. And so this work has been extended, next slide, to several substrates, styrenes, acrylates, pentanoates, and terpenes. And so on the proton, the max that we're able to get right now under unoptimized conditions is with ethyl pentanoate, and we get up to 150-fold signal enhancement on the proton NMR. And for isoprene, which is a substrate Allison showed you all yesterday, we get up to 100-fold signal enhancement on carbon-13 NMR. And so we didn't want to stop there. We wanted to kind of look at some of the traditional substrates that have been used in Saber. And so those often feature nitrogen-based substrates or substrates with a lone pair to be able to donate into the metal. And so we tried our hand at those. Next slide. So taking pyridine as well as other nitrogen-based substrates, and they simply just don't provide any polarization. And so our working theory is that nitrogen-based substrates actually compete with the binding site of pure hydrogen on our complex. So if you look to the right, you see that that nitrogen-based substrate is binding in the same position that pure hydrogen would bind, while olefins like to access that axial position there, and so they're more susceptible to being polarized. So next slide with that, I'll conclude with just general. We have shown you all a cobalt Saber catalyst and demonstrated it with olefins. We've shown you some of the enhancement, and future work is really going to be on trying to optimize these catalytic conditions, maybe the development of future cobalt catalysts, as well as trying to get enhancement up to the point where we can apply them as contrast agents. So next slide. I'll thank my group. I'll thank our collaborator, Simon Boyd Goodson, as well as thanking you all for your attention. And I look forward to any questions in the poster session.
Fantastic. Thank you so much. Okay, we are on to the next. Start whenever you're ready.
All right. Hello, everyone. My name is Tommy Lang. I'm an undergraduate student studying chemistry at Duke University. And my lightning talk today is about virtual reality understanding of the catalytic mechanisms in SABRE through density functional theory calculations. Next slide, please. So to begin with, I'd like to give a very brief introduction. The goal of our study is to elucidate the para-hydrogen exchange mechanism in SABRE. And the methods that we utilize is electronic structure calculations. To be specific, we calculated the minimum energy reaction pathways using the string method, as well as the climbing image technique. The level of theory that we use is density functional theory that includes dispersion interactions. For those interested in the technical details, the code package that we use is FHI-AIMS, which uses numeric atom-centered basis sets. And the whole set of methods has the advantages of, first of all, having very high numerical precision. And secondly, it uses all electrons in the system, which includes core and valence electrons. And lastly, it has high computational efficiency. Next slide, please. Now I'm going to present a video that shows the key idea of a very important reaction pathway in the system. On the left, we have the geometry, and I have highlighted polarization in orange. And you can see the para-hydrogen from the solution is undergoing this pyridine hydrogen exchange reaction and starts to bind to iridium, and the pyridine leaves and flows into the solution. On the top right, you can see the energy diagram, and the cursor is moving as the animation progresses. And now it undergoes a process so-called the hydrogen hydride exchange, where in this case, the para-hydrogen molecule splits into two para-hydrides. After a series of more transition state, it undergoes another hydrogen pyridine exchange reaction. But in this case, the pyridine from the solution exchanges with the ortho hydrogen, and it leaves. What we get here is an ortho hydrogen flowing in the solution. So I do want to point out that this process is very important in the refreshment of polarization in the catalytic system. Next slide, please. I want to click again. Yes. So I do want to point out that the video that you just saw was a small part of a larger reaction network investigating our study. Here I've highlighted the reaction cycle using blue arrows on the bottom right here. So this is a holistic presentation of the energetics of the entire reaction network. We have each of the stable intermediate states labeled corresponding to their relative single point energies on the y-axis, and each of the reaction arrows color-coded according to the heat map and their minimum energy reaction pathways. The transition state energies are also labeled above or below each of the arrows. So you must, as we must have realized at this moment, analyzing the energetics of this reaction network could be quite complex if we do it manually. That's why we introduced virtual reality to our study. Next slide, please. So here I'm going to present to you a very short clip of the video of one of our co-authors playing around with the virtual reality perspective. Here we can see on the left is the reaction network, and here on the right is a static snapshot of the video that you just saw. And in the middle, you will see the geometry, which you can animate using the joystick from frame to frame. The perspective here is a little skewed. It's actually looking up from the axial pyridine of the catalyst. So thank you. This is my presentation, and I welcome everyone to join me at my poster session where I will get into the details of the methods, the results, and the conclusion of my study. Thank you.
Fantastic. Thank you so much. Okay, we have our final presentation this morning.
Hello, good morning, everyone. I just want to say thanks for having me. It's been a real pleasure so far seeing all the talks. So my name is Erik van Dyke, and I want to talk briefly about the work that I did as an undergraduate at the Pines lab, where we looked at the polarization buildup and decay of vinylated fatty acid precursors. Next slide, please. So why do we choose fatty acids? Well, first, fatty acids have been known to play a role in diseases such as metabolic syndrome, certain forms of cancer, and bowel disorders. Acetate has already undergone development for use in hyperpolarized magnetic resonance spectroscopy. So my idea is that expanding our repertoire of biomolecules that are amenable to FIP could give us glimpses into other biological systems. And also our experimental setup allows us to look at the kinetics of the polarization buildup and decay, because we can supply a constant flow of parahydrogen, which helps sort of simplify the kinetics of the system. So next slide, please. So I want to give you a brief overview of our setup. We used a parahydrogen generator that cools the thermal hydrogen over an iron oxide catalyst to 20 degrees Kelvin. The flow is then controlled by a mass flow controller, which feeds our parahydrogen into a capillary, which then is inserted into our sample. And the capillary is left in situ as we take our spectra. We can vary the pressure using an inline pressure controller. We looked at pressures anywhere from 1 atmosphere to 7.8 atmospheres using a solvent system of deuterated chloroform and deuterated methanol. We looked at vinylated fatty acids, 4, 5, 10, and 12 carbons in length, but we really focused on the fatty acid 4 carbons in length, which is a vinyl butyrate. We used a standard rhodium catalyst as our FIP catalyst, and all measurements were taken on a 1.4 Tesla benchtop spectrometer. And next slide, please. So here are a couple of sample spectra that we were able to obtain on our benchtop. So you can see the difference between the thermal signal after one scan and our hyperpolarized signal. We used both Altadena and Pasadena, with Altadena being used first when we had more people available in the lab, because there was this more logistically challenging bubbling at Earthsfield and then placing in the spectrometer and then triggering the spectral acquisition. So with the COVID restrictions, we opted to go for a simpler system. Just using the Pasadena model, we were able to leave the tube in situ for bubbling inside the spectrometer and vary the bubbling timing using a programmable solenoidal valve with automatic spectral acquisition as soon as bubbling was done. So we took, I think, about 216 samples overall of vinyl butyrate, and we were able to kind of vary the substrate concentration and the catalyst concentration to map out the signal and the enhancement according to the molar concentration. Next slide, please. So as others have said, optimizing a FIP experiment depends on creating the greatest sort of molar polarization, the emerging idea. And so we were attempting to do that in this study, sort of inadvertently. So to create the optimal molar polarization, it's helped by building a model. So we attempted to do that by constructing the scheme on the left. Next slide, please. So using this equation here, which has been derived by others before to fit our data, we still saw sort of not an optimal fit here. So we were attempting to create a better fit by taking into account the dissolution of hydrogen, which isn't accounted for in this model here. And so that's where we're at right now. And looking forward to answering any questions in the poster session. Thank you.
Fantastic, and thank you for keeping the time. So we are now at the stage where we are going to go to the breakout sessions. Remember, the links for each of those posters are in an email that you should have received last night and also in the hashtag general channel on the Slack. We will reconvene in this room at 1320 UTC. All right, I will see you all in the posters. I hope you all enjoy them. And thank you again to our speakers who did an amazing job presenting with a very strict timing. And I apologize for my harsh use of the mute button, but now we're still on schedule, so it allows us an hour in the break rooms. Okay, we'll see you here at 1320 and see you in the poster rooms now.